Okay, so one sample hypothesis testing. We're going to talk about sample means today and sample proportions. We might get to sample proportions today. But in this chapter, what we hope to learn is the basic principles of hypothesis testing, how to use hypothesis testing to test mean or proportions, what are the assumptions of each hypothesis testing procedure and how to evaluate them, and the consequences if they are seriously violated. Then we want to know how to avoid these pitfalls involved in hypothesis testing, and then some ethical issues associated with hypothesis testing. So what's a hypothesis anyway? Educated guess, right? It's the first thing they teach you. It's an idea, a claim, right? That's really what it is. It's a claim. So a hypothesis is a claim or an assertion about a population parameter. Now the key thing about this claim is that it has to be testable. So you could say that something like, I have a hypothesis that the sky is purple. Right? That's a claim. A false one, but still, it's a claim. As long as we can test it, you can do it. Things that you can't test really aren't legitimized as hypotheses. Right? It has to be a testable claim, something that's a positive statement. Positive statements can be lies, as long as they are factual statements. Normative statements are a lot harder. Should we do this? Should we do that? Those are not very good hypothesis statements. Because, the should depends on who you are, right? So a population mean, for example, the mean monthly cell phone bill in this city is $42. That could be totally false, but we can test that, right? We can test whether or not the mean in this particular city is $42. Population proportion. The proportion of adults in this city with a cell phone is 68%. Again, that's a claim that we can test. So in this chapter, the mechanics you've already learned. That's what we did in the previous two chapters. What we're going to learn instead in this chapter is a lot of vocabulary. Right? So one, there's a null hypothesis. Think of this as the current standard. All right? Whatever is the current standard, that's what we're going to call the null hypothesis. So this states the claim or the assertion to be tested. The average number of TV sets in the U.S. home is equal to 3. That is the null hypothesis. That is the claim. We want to see whether or not this claim is true or false. The hypothesis is always about a population parameter. It is not about a sample statistic. So whenever you write down a null hypothesis, or any hypothesis for that matter, it's going to be represented by the population parameters. So you're not going to be using X bar is equal to something. Right, so we begin with the assumption that the null hypothesis is true. That is the assumption. You're saying that this claim is true. Can we provide evidence against it? Now this is important. I want you to think of these steps as if you're in a trial. All right? When you're in a trial and you have a guilty or not guilty plea, are we ever really saying that you're innocent? We're just saying you're not guilty. And when we say you're not guilty, what is usually the terms we say after that? And they usually say there's insufficient evidence to say to the contrary, right? There's not enough evidence to show that you're guilty. That doesn't say that you're innocent. It's just that there's not enough evidence to show that you're guilty. In the same way, we're going to proceed. We're going to say, here's our claim, our null hypothesis. Is there enough evidence to reject the null hypothesis? If there's not, then all we can say is that there's not enough evidence, right? For what we have, the claim seems to be true. Some characteristics, generally refers to the status quo or historical value. We're always going to contain things like equal to, less than, or greater than sign, and may or may not reject in those cases. So when we're going to test this null hypothesis, we're going to come up with an alternative hypothesis. And the alternative hypothesis says, okay, we're not equal to that value. It doesn't say in which direction. It just says we're not equal to that value. Or we are less than that value, or we are greater than that value. Alright, so the alternative hypothesis is the opposite of the null hypothesis. So the null hypothesis says that the mean number of TVs is equal to 3. The alternative hypothesis is that it's not equal to 3. Alright, so if our claim is that you are not guilty, the alternative hypothesis is that you're guilty. And again, we can follow the same characteristics that we have with the null hypothesis, that it can contain equal to, less than, or not equal to, and may or may not be proven. So these are the steps that we're going to follow for a hypothesis test. You're going to notice that they follow the scientific method pretty closely. Number 1, develop a null or alternative hypothesis. Alright, so come up with a claim. Come up with your question. Number 2, specify the level of significance, alpha, and the sample size. This is developing your experiment to test said claim. Step number 3, collect the sample data and compute the test statistics. The test statistics include things like the sample mean, sample variance, sample standard deviation, and in our case, when we actually want to do testing, either a Z or a T statistic. Alright, so here we came up with a question, here we designed the experiment, here we collected data from the experiment, and now we're going to do analysis. Alright, so we're going to determine the critical value such that the null is rejected. And in step 5, we come to a conclusion. We determine whether or not said null is rejected, or if we fail to reject the null. Now notice I use that word, that phrase, fail to reject the null. Going back to our example of the case, I have insufficient evidence to say that the null is false. So, here are a couple of parts of hypothesis testing. This is a one-tailed test, where we're saying that the alternative hypothesis is that the true mu is less than the claim. Here is a upper tail test, where the true mu is greater than the claim. And here's a two-tailed test, where we're just saying that the true mu is different than our claim. And it could be either higher or lower. What you should keep straight in your head is that whenever you have an equal to and a not equal to sign, that's essentially a test using a confidence interval. And you're saying whether or not the claim falls inside of that confidence interval. When we do a one-tailed test, it's a little different. And we're going to see some pictures on how to do that. But it's still similar to this idea of finding a confidence interval, finding a rejection region. Alright, so the critical value. For the assumed population mean, if the sample mean is close, the hypothesis, the null hypothesis, is not rejected. So all this is saying is that if you go out and you find a Z statistic, and the Z statistic is something that is very small, that's saying you're pretty close to the actual null hypothesis, right? You're pretty close to the claim. If that's true, you really don't have that much evidence to reject it, because there is some noise in collecting any sample mean. And we showed that before. But if you're far away from that claim, say 3 standard deviations away from that claim, it's tough to believe that that null is true. Right? Because there'd be less than a 1% chance that that null still belongs in that distribution. So this is where those T and those Z statistics matter. And know why those values that I used to give you before of 2 and 3 matter. Anything that's 3 standard deviations away is highly improbable that belongs in that distribution. So what you should be thinking about is that if you have very large critical values, you're more likely to reject. If you have very small critical values, you are less likely to reject. Alright, so about how far is far enough in order to reject? That kind of depends on you. This is where you have to determine that level of alpha. What is the level of confidence you're willing to have? What is the level of confidence you're willing to have to say, yes, this is different from the claim? And that's where those alphas of 1%, 5%, and 10% come in. Alright. So our sampling distribution of the test statistic, if we're doing a two-tailed test, so that means an equal to or not equal to test, and we come up with a test statistic, a t, an observed t. If that test statistic falls into one of these blue regions, that means that we're far enough away from the claim that we don't think that the claim is true. So again, if you're a visual learner, I would always draw these pictures and I would highlight what the rejection region is. Right? The moment that your observed test statistic falls into the rejection region, you can reject the null hypothesis. If it sits inside of the rejection region, so anywhere in here, in the white, then you fail to reject the null hypothesis. You don't have enough evidence to say the null hypothesis is false. Okay, so there are two types of mistakes that we can make. The first one we actually choose. Right? The first one is the amount of mistake we're willing to accept when we reject a true null. Now we choose this mistake. This is our alpha. We know what this one is. So if we set alpha to 1%, we're saying that we're going to allow ourselves to be wrong 1% of the time. So if we choose alpha to be 5%, we're going to allow ourselves to be wrong 5% of the time. We get to choose this one. A type 2 error is a lot harder. A type 2 error is the error of not rejecting a null hypothesis when it's false. So this is the false positive rate. Alright. Now we can actually find out when we can fall into these two types of errors. A type 1 error occurs when the null hypothesis is true, but we reject it. That's a type 1 error. Null hypothesis is true, we reject it. A type 2 error is when the null hypothesis is false, and we do not reject it. In other words, we're saying that it's true. So one of the language that I use whenever I'm trying to do this testing, just to cover my bases, is that I almost never say I accept the null hypothesis. I just say I reject or I fail to reject. Going back to the example of the court case, I just don't have enough evidence to say that it's not true. I'm not going to say it's true. There's not enough evidence at this time to say it's not true. So here are some possible results for a hypothesis test. The confidence level is going to be 1 minus alpha times 100%. So that's where you hear my 99% confidence level, my 98% confidence level, 95, 90. The confidence coefficient is 1 minus alpha. It's the probability of not rejecting the null hypothesis when it's true. And the power of a statistical test is 1 minus beta. Now, let me tell you why we developed this tool to begin with. The way a lot of the tools in statistics are developed is that a researcher will start off and they will actually create their own data set, meaning that they get to play God for a second. Right? They get to choose what the values of the true population parameters are, and then they will simulate samples from that population. And I did that once in class already, where I had 150 different observations, and I started drawing means from that sample. Right? I created that sample, so I knew what the mean was ahead of time. I knew what the variance was ahead of time. And then what they'll do is they'll develop tools to predict what the true mean is by using samples. So they'll use this to see how good their model is. If their model has very, very big power, meaning that beta is really small, that's a very good model to use. On the other hand, if beta is very, very big, that's a terrible model. You want to trash that thing. Right? But those are the only times where you could really know. In most cases, you have no idea how big your beta is going to be. So type 1 and type 2 error cannot happen at the same time. Think about that. We go back a couple of slides. Can you ever be here and here at the same time? Can you ever not reject a false null and reject a true null? You can only be in one place at any one time, right? A type 1 error can only occur if the null is true. A type 2 error can only occur if the null is false. If a type 1 error probability increases, then a type 2 error probability decreases. So as alpha goes up, beta has to go down. This is the trade-off that you have between those two. So if you're willing to make alpha really, really big, well then your power is going to go up. But by doing so, you're more likely to fail to reject a false null. However, if you expand alpha out, so you make alpha really, really small, you're more likely to accept a false. So here's an example in a picture. All right, so it's as easy as I can make it. Here's a guy. As far as we know, men can't get pregnant, right? So, type 1 error is a false positive. You're pregnant. Remember, this is the dude. Can't get pregnant. All right. Here, you have a false negative. You're not pregnant when she clearly is. Right. That is the difference between the two. So how do we do hypothesis testing for a mean? If we know the standard deviation of the population, which you know that, we're going to use a z-test. Because the moment we know that, we know it's normally distributed, and we can use a z. Or no problems there, right? If we don't know that, which is almost always, you're going to be over here doing a t-test. Right. These are the same rules as the last chapter. All right, in the last chapter, if we knew sigma, we could use a z-test. If we didn't know sigma, then we'd use a t. So then the approach is still to find the critical value and then calculate a p-value. You can do the same thing with a t-test, only it's a bit harder with those tables. So the critical value approach is, first, you find the critical value for your test. So step one, what you do is you write down, again, your null hypothesis and your alternative hypothesis. That's what we did here. Then you specify the level of significance and the sample size. So here's our level of significance. I gave you the sample size of 25. You use that to calculate the critical values. So you collect the sample data, compute the test statistic. N is equal to 100, x bar is equal to 2.84 in this example, which gives you an observed z-statistic of negative 2.0. What I mean by observed is that you use the values from the problem. Then you determine the critical value. Here our critical value is going to be 1.96 since our alpha was equal to 0.05, which means we want a 95% level of confidence. And then we compare the 1.96 to the 2.0. Alright, so the 1.96 would be here and here. Given that we have a negative 2.0, are we in the rejection region? The two-tailed test, so we're going to have positive 1.96 and a negative 1.96. Given that our observed statistic was negative 2.0, are we in the rejection region? Yes, we are. So we can reject the null hypothesis here. Alright, so in a picture, you would have 1.96, negative 1.96, and positive 1.96 here. You calculate your observed z, which happened to be negative 2, so it's in this blue area. So you reject the null hypothesis. Sufficient evidence. There is sufficient evidence that the mean number of TVs in the U.S. homes is not equal to 3. Alright, so this is all the parts on means. We can do the same thing for a t-statistic. Right, for a t-statistic, you would use the same rules. And I'm going to show you an example of it, but for a t-statistic, you're going to do the same thing, except for t's, you're going to have t's. And they're just going to be a little bit wider. But the rules are going to be exactly the same. Now, if you don't like this method, where you find the critical value for z, there's another method called the p-value method. P-value method works in a similar way. Instead of comparing these observed z's and finding out if you're in this area, what you're going to do is compare the observed probability. So what is the probability of our observed z being greater than or less than the alpha? In other words, if I find the probability of my observed z being minus infinity up to that point, is it greater than or less than the alpha amount? If it's greater than the alpha amount, it implies that we must be on this side. of the rejection region. If it's less than the alpha amount, it implies that we have to be inside of the rejection region. So if I tell you that the p-value is 0.01 and our alpha was 0.05, that implies the z must be in those tails. So the p-value approach says we're going to still calculate our observed z statistic. So we're still going to go out and find that -2, but then we're going to say what is the probability of being less than or equal to -2. So we'd have to go to the z table and we'd have to calculate it. All right, this sounds like a lot more work. All right, and it is more work when you're the one doing the work. But when your computer's doing the work, it's actually a lot easier to compare p-values to the alpha, because the computer is going to compute the p-value for you. So we compare the area under the curve for the test statistic and the critical value. This green area here is alpha, so that's the level that we chose. And if this z stat here is our observed z stat, we would want to find the probability of being greater than or less than that z stat. So we'd have to go to the table. If that p-value is greater than this green value, that must mean that we're inside, so we're not in the rejection region. All right, so here's the smaller green value, which is alpha. In this case, here's the larger p-value. So in this case, we would fail to reject the null hypothesis. We don't have enough evidence. If the p-value was smaller, though, we would reject the null hypothesis. So if p-values are less than alpha, we reject the null. If p-values are greater than alpha, we fail to reject the null. Another way of thinking about it is that the p-value essentially says, what is the probability of accepting the null hypothesis? As that probability gets smaller and smaller, you're more likely to reject. As that probability gets larger and larger, you're more likely to accept. So in the example we showed you here, the p-value is clearly larger than the alpha value. So we're going to fail to reject the null hypothesis. If our z statistic, on the other hand, is on that right side of the critical value, then the p-value would have to be less than the alpha value. And if the p-value is less, we reject the null hypothesis. The other way you could do a two-tailed test is that you can construct your confidence interval. So you can use your mean of 2.84. In this example, again, use the 1.96. That was our critical value. And then just construct the confidence interval. Once you get there, all you have to do is ask the question, does the claim fall inside the confidence interval? If it does, you fail to reject the null. That means you're inside of the rejection region. If the claim falls outside of the confidence interval, you reject the null hypothesis. All right, remember again what the confidence interval represents. It says that if you were to do this 100 times, 95% of the time, the actual population mean will fall inside of it. So with 95% confidence, if the claim falls outside of it, that means it's not part of that population. All right. So how do we do it when we're in the real world? We're over here at the t-statistic place. In the real world, we don't know what sigma is, so we can still use a critical value approach or a p-value approach. The p-value approach on your end is even more cumbersome because you generally don't have p-value tables for student t. However, you can get them. Now, you have Excel. Excel does have the t-distribution inside of it, so it can produce those probabilities for you. It's just more work. If you're going to do this out in the real world and you have a sophisticated computer, you're more than likely going to have a software package that will just spit out these p-values for you, like I showed you on that one web page. If you don't have that and all you really have is Excel, usually this way is the better method. Find the critical value, find the observed value, and compare the two. So if the population standard deviation is unknown, then you use the sample standard deviation S. You use the t-distribution instead of z, and you must assume the population you are sampling from has a normal distribution. Otherwise, all the other steps, concepts, and conclusions are the same as sigma known. Alright, so the average cost of a hotel room in New York City is said to be $168 per night. To determine if this is true, a random sample of 25 hotels is taken, which results in a mean of $172.50 and a standard deviation of $15.40. Test the appropriate hypothesis at alpha equal to 0.05. First, what is the claim here? What is the null hypothesis?
The average cost for a hotel room is $168 a night.
That's right. That is the claim. That's our null hypothesis. What is the sample mean here?
172.
The 172.50, yes. And then our sample standard deviation is 1540. All right. These are statistics. All right. These are statistics. This is our claim. So we would develop the null and alternative hypotheses, which is equal to 168 or not equal to 168. We would then use our sample size of 25 and our alpha of 0.05. We would then construct our observed t. Whenever I say observed t, I'm saying you're using the information from the sample to construct the t statistic. This is not the critical t. The critical t, you don't need to know much of anything about the problem except for its sample size. You don't really need to know anything else besides that. So for the observed t, we're going to construct it the same way we did in the last chapter. We take the sample mean, subtract it off from the claim, divide through by the standard error. Here our observed value is 1.46. Okay? This is our test statistic. Then we need to go to the table and find the critical value. We went ahead and we found in the beginning of class the t statistic associated with a sample size of 25, which gives you 24 degrees of freedom. We want it to be a 95% confidence interval. It's the same thing we're asking here, right? So we found that it was 2.0639. Now we have to ask the very simple question. Is this bigger or less than this? So in other words, does this 1.46 fall in the rejection region? Again, if you're a visual learner, draw the normal distribution. First put the critical values in, which is this negative 2.0639, this positive 2.0639, and say, does this fall on the inside or on the outside?
Inside.
On the inside. So if it falls on the inside, can we reject the null hypothesis? No, we cannot. All right, so we fall inside. We're in here. So we do not reject the null, and there is insufficient evidence that the true mean cost of a hotel room is different than 168 per night. Again, notice the wording we use there. We never say we accept that the average cost is $168 per night. We just say there's not enough evidence to say that it's not true. Again, the danger of saying that it's true is that you're going to commit a type 2 error. Alright, so the p-value approach. For the p-value approach, you still have 24 degrees of freedom. You still have to go back out and use the table. So your t-stat would be 1.46. And then you'd have to try to calculate the p-value using a table. That is virtually impossible. So let me show you how you do it in Excel. And you can do the same thing for a z-table. So for those of you doing it on your homework assignments and you want to know the exact values, you can use the same steps for z's. So if I want t, I want t distribution two-tailed. Okay, so that's t.dist.2t. It's two-tailed. When I do that, it's asking me for x and the degrees of freedom. X here is going to be your observed t, the one you're using, so our 1.46. Our degrees of freedom are the same degrees of freedom you've calculated all this time. In this case, it was 24. You do that, it tells you how much probability is left in the tails. In this case, it's 15,725. So the p-value here would be 15,725. If you compare that to an alpha of 10%, do you reject or fail to reject? You fail to reject, right. And you'd still fail to reject at 5%, and you'd still fail to reject at 1%. Let's push it out a little bit, though, so that we can see how this works. If I make it 2.1, would I reject the null hypothesis at the 10% level?
Yeah. Yes.
Yes. How about the 5% level? All right.
Reject.
How about the 5% level? Would we reject?
No.
Yes, we would. All right. Alpha is still bigger than the p-value. What about the 1% level? At the 1% level, we would not. Now, here's something to be careful about when you use computers in order to do this exercise. In some cases, they only tell you the area in the tail. In other cases, they tell you the full areas of both tails. This one, they tell you the full areas of both tails. So this one, you can compare alpha, the full level of alpha, to this full level here. If they don't tell you that, you have to do the calculus in your head real quick, saying, okay, if I'm only looking at one tail, meaning that the full alpha is sitting in one tail, and I use this 2t instead of just the regular distribution, I've got to split that in half. Right? Be careful, and this is why we're drawing the pictures helps. Because if you're doing a one-tailed test, all the probabilities in one tail. You don't have anything in the other tail. If you're doing a two-tailed test, this works fine, right? But be careful about that, and it changes from software to software. So here we compare the p-values to alpha and state that the managerial conclusion is that since 0.10 to 0.20 is greater than alpha equal to 0.05, we do not reject the null hypothesis. All right, comparison of the two-tailed test and the confidence interval. You'd construct the confidence interval the same way we did in the last chapter. You'd get the critical t-value. You'd get the standard error. You multiply the two of them and you add and subtract it from the sample mean. Again, if your mean falls inside of there, which it does in this case, right? 168 was our claim. $168 was our claim. That falls inside these two values. You would say that we don't have enough evidence to reject. If I told you instead that the claim was 160, then we could reject. Right? At 160, we're outside of that confidence interval. So we can say it is different from the claim. All right, so up to this point, we've done only two-tailed tests. We haven't done a one-tailed test yet. We've done two-tailed tests. We've seen how we can do it with a Z, and we've seen how we can do it with a T. So far in the two-tailed case, if you didn't want to learn too much, you could always revert back to the confidence interval and just say, all right, does it fall inside the confidence interval or does it not? Once we go to the one-tail example, we can't do that anymore. All right. Once we go to the one-tail example, we have to use either the critical value method or the p-value method. Again, in class, it's almost always easier to use the critical value method because it's just a comparison of two observable things. You don't really need to know what the probabilities look like. When you have a computer, it's usually easier to use the p-value method since the computer is already generating that information for you. So here we are, one-tailed test. We're asking the question, is the null hypothesis greater than 3? Or the alternative is that it's less than 3. Is the null hypothesis less than or equal to 3? Or is it greater than 3? Here we're looking at the lower tail, and here we're looking at the upper tail. The way you know which tail you should be looking at is by looking at the alternative hypothesis. So if it's less than, you want lower. If it's greater than, you want upper. And the goal in testing is to really reject the null hypothesis. And usually the null hypothesis is a comparison to 0 if you're looking at anything else. So if you're trying to find whether or not a drug works, 0 is the baseline. And 0 is, I am not on the drug. So you want to see whether or not health improves relative to the baseline. So can you say you're different from 0? Now, different from 0 in a clinical trial could mean two things, right? It could mean that you are better. It also mean that this thing should never hit the market. Right? That's not a very good test there. Instead, you'd want a one-tailed test. Not only are you different from 0, but you're better than 0. So, there is only one critical value when we're doing a one-tailed test. We don't have to split it up anymore. There's only one critical value we need to find. We're still going to compare our observed value to that critical value. We're still going to check to see if the observed value falls inside of the rejection region, but we only have to calculate one value this time instead of two. The rules still apply. If our observed z-stat is past the critical value, we reject the null hypothesis, and if it's not, then we fail to reject the null hypothesis. If we do our one-tailed test going in the opposite direction, then again we want to reject if it falls in the rejection region, and fail to reject if it falls in the white region. So here's our example. The phone industry manager thinks that customer cell phone bills have increased and are now over $52 per month. We wish to test this claim. So here, the assumption or the previous status quo is that they haven't gone up. Previous status quo is that they haven't gone up, or if anything, they're lower than this $52. And he wants to see, no, is it greater than that $52? That's the evidence they want to find. Is it greater than that $52? I'm going to specify level of significance. In this case, we're going to say alpha is equal to 0.1. And again, because the square root of 25 is easy, we're going to use a sample size of 25. And we want to do a test here. Now, we haven't been given enough information yet to find our observed statistic, but we should be able to find our critical value. Right? So if our critical value is alpha equal to 0.10, we can go to a z-table now and find what that optimal z is. So I want 10% in one tail. What's 10% in one tail? 1.282. 10% in one tail, all the way down to the bottom, 1.282. So this is saying that if we were to draw a normal distribution, I want 10% in this tail. Alright? The z associated with that is 1.282. So that is our critical value. In order to be sufficiently greater than, our observed statistic has to fall inside of here. If not, we can't say that bills have actually increased significantly. So we observe a sample mean of 53 and 10 cents and a sample standard deviation of $10. Let me show you where we get this 1.3178 from. So we have sample size of 24. We still want 10% in the tail. So that's this value right here. 24 degrees of freedom, 1.318. And then we compare that 1.3178 to our observed value. That's the sample mean minus the claim divided by the standard error. You get an observed value of 0.55. We failed to reject. And we're here. Here was the critical value. We needed to get in here. We weren't in there, so we can't reject the null hypothesis. So there is insufficient evidence that the mean monthly cost of a cell phone is greater than 52. So yesterday we did sample means. We looked at sample means when we have a large sample or when sigma is known. Sample means when we have a small sample or when sigma is not known. And we were able to construct both one-tailed and two-tailed tests with doing using those statistics. Today what we're going to do is we're going to look at proportions instead. Now, proportions are going to act very much the same way as the means did, but there are one or two wrinkles that we have to be careful with when it comes to proportions. Okay? It's still true that P is the point estimate for the population proportion. Population proportion we call pi. Yes? And P still represents the proportion of successes. So you want the total number of successes in the numerator over the total number of options in the denominator. So number in category of interest in sample divided by sample size. We can only use a normal approximation when we are satisfied with the rule that n times 1 minus pi or pi times n is greater than 5. We talked about some restrictions associated with that rule. We can't do things where pi itself is either really close to 0 or really close to 1. In those cases, this rule is going to be violated. Right? So, we can just throw out those two endpoints, for example. If we throw in 1, there's no way we're going to meet this requirement. And if we throw in 0, where we have the other condition, there's no way we're going to meet that requirement. So these are mainly going to be proportions that are somewhere between 0.3 and 0.7, where they become useful. Outside of that, you need a really, really large sample size to get over that hump of 5. Okay? Now, we're still going to be using our P as our estimate for pi. Pi here is the population parameter. And you're going to notice that here's the one key difference. What are we using to calculate the standard error? Are we using P or are we using pi?
Pi.
Pi. Now, pi is the claim, right? Pi is the hypothesis here. That's the one part that's a little different from the sample means. In the sample means, again, we usually didn't have sigma, so we used S squared instead, right? Well, here, they're going to give us pi. They have to, right? Otherwise, we're not testing anything. They're going to give us pi. So when we go and we calculate the standard error, we have to use pi in order to do that. That's going to be a little bit confusing because you're going to want to use p in there. Your brain is going to want to say, no, we have to plug in p. But this is how we would construct a z-statistic. You take your point estimate minus the claim, and then you use the standard error assuming that the claim is true. In other words, that pi really is the population proportion. This is what's different from when we do it with a sample mean. With the sample mean, again, we typically don't know what sigma is, so we use the sample estimate in that case. Right? Even though we're still testing mu equal to some value, we have to use the sample estimate in that case. Here, it's a little different because we're given a claim and we can use that claim to calculate the standard error. I'm repeating it again and again and again because you're going to make this mistake if you don't check it out. All right? You're going to be drawn to using P, sticking in there, and going about doing it when that would be wrong. You have to do it assuming that the null is true. Right? An equivalent way of doing the same test would be to take a full value of x, subtract off the expected value of x, and then divide through by standard error. This here is a binomial. Right? The expected value of a binomial is n times pi. Right? And then the variance of a binomial is n times pi times 1 minus pi. So then the standard deviation of a binomial will be the square root of that. You can do it either way, but typically you're not given x. You're given instead a proportion. So here's an example. Marketing company claims that it receives 8% responses from its mailings. To test this claim, a random sample of 500 were surveyed with 25 responses. Test at the alpha equal to 0.05 significance level. So first we got to check, can we do it? Before you do anything else, start there. Can you do it? Because if you can't, then don't waste your time calculating anything else. So we take the 500, we multiply it times the proportion of 8%. When we do that, we pass the upper bound test, and we just have to be greater than 5. We get 40 here. And we pass the lower bound test. 1 minus pi and multiplying times 500. So we're good. We can use this as an approximation. Next thing we need to do is go out and get some data. Well, we go out, we sample 500 people. With those 500 people, we found that 25 responded. All right, so we're going to take 25 over 500. That's going to give us a proportion of 5%. The claim is at 8%. So we subtract off the claim of 0.08. And then we calculate the standard error using that claim of 8%. So you have 0.08 times 1 minus 0.08 divided by the sample size, and we take the square root of that. After that, it's all back to the same stuff we did with sample mean. Here's a z-value, you find critical z-value, check whether or not you're in the rejection region. So, if we're doing it at the, I think it was 5% level, right? Yeah, we're doing it at the 5% level. We're doing an equal to, and that should be a not equal to sign there, so a two-tailed test. That means that our z-value is going to be 1.96, just like we had in the beginning of class. So does this negative 2.47 land in the rejection region?
Yes.
So then we reject the null hypothesis. We can do this with p-values as well. So for p-values, what you do is you go to a z-table, find that negative 2.47. So we're going to go and try to find this 2.47 here. Here is 2.4, and we want to go all the way over to 7. That gives us a probability in the tail of 0.0068. Okay? Now, this is a two-tailed test. Since it's a two-tailed test, we actually have to multiply that p-value times 2 in order to compare it to alpha. Either that or take alpha and divide it by 2. whichever way you want to do it. If we do that, we're going to get, what is that?
0136.
Yeah, 0.136, and we're comparing that to 5%. Which one's bigger?
5%.
The 5%. So again, we reject the null hypothesis, right? P-value smaller than alpha, we're good. One thing I want you to notice is that whenever you're using the proportion, you're using a z statistic. In other words, there's no such thing as a small sample for a proportion. There are a couple of reasons of why that holds. The two main reasons is that, one, in order to satisfy the normality constraint, that you have to be greater than 5 on those two constraints, and is pretty large, right? Something way bigger than 30. And then two, because you're using the null hypothesis to calculate the standard error, it's as if saying you know what the standard deviation is for the population. And we've already shown before that if you know what the standard deviation is for the population, you can use normality. Right? So those are the two reasons that you're always going to end up using z when we talk about proportions. That's not true when it comes to sample means. Alright, so here's some potential pitfalls to consider. You use randomly collected data to reduce selection bias. Do not use human subjects without informing them. That's a key thing. IRB kind of frowns upon that. To be fair, IRB is different from country to country. There is a couple of experiments they've tried to run on figuring out what makes people harder bargainers and not. So there's this guy out in, it's one of the California schools. It'll come to me.
UCLA.
No, it's down south. It's outside of, it's the one that's near USC, but it's not USC. No. It'll come to me later.
Some college.
Yeah, it'll come to me. It's another expensive college in California. All right. His name is I think Zach Brax, and he actually came here and gave a talk. He does neuroeconomics, and what he wanted to do was find out what makes people more aggressive. So there's a game in economics called the ultimatum game, and in the ultimatum game, it's really simple. We're going to split up a pie or a pot of money. I make an offer, and you either accept or reject my offer. Okay? So I say this is the split for the money, and you either accept it or reject it. Now, if all you cared about was being better off than you were when you walked in, you'd accept a penny, because that'd make you better off in theory, right? But, humans have this thing called spite. And so whenever they hear very low offers, they tend to reject, right? And because of that, it kind of pushes a lot of people to split 50-50. So we want to know what causes that, and also can we get you closer to the economic outcome. So what he decided to do was use two drugs, two hormones actually. One is oxytocin, which if you don't know is called like the love drug or the love potion. And he wanted to use that on students. The IRB in California didn't take kindly to that. So he had to go to Germany, and apparently Germany has no problem with shooting up students with oxytocin. So he went to Germany, shot up a bunch of Germans, hopefully not during Oktoberfest, and he found that when you do this, they do share more often, and they're more willing to give. Why is this important? Well, they now make oxytocin in an aerosol version. So have you ever walked through a department store and you're kind of hit with that smell of perfume and everything else? So think about that, right? You could actually spray this in a department store and it'd make you more willing to buy because you're happy that you're there and everything seems so much more fun. And, it'll also probably become a new dating scene because everybody will be underneath the love drug at that point. But you have that. And then he wanted to see the other side. So the other side was, how can I make people more aggressive? Well, testosterone. So he went ahead and he shot up both males and females with testosterone. When he did this with males, there was virtually no difference in their bargaining before and after, but females became extremely aggressive once they got hit with testosterone. Again, German students. And so this human Subject's information is very important, but there are different places that you can go to do that if the U.S. doesn't permit you. You have to choose your level of significance alpha and the type of test, one tail or two test, before the data collection. That's more of just an ethical standpoint. You don't sit there and run all the tests and then say, well, if I kind of switch my test, I now get a significant result. That's not really the question you went into with it. So that's the ethical part. And then reporting all pertinent information regarding statistical significance is also important. What we mean by that is if you're going to do both a one-tailed test and a two-tailed test, and you find that you're significant in one and not significant in the other, you report both. That's the ethical thing to do. To say that, okay, we do find some significance, but only in a certain area. Now, why might that be important? In medical trials, often all they care about is the bottom line average effect. But for certain drugs, certain people have a higher response to these drugs than others. A great example are antidepressants. Right? Antidepressants, some people can take one particular antidepressant and it doesn't do anything for them. If anything, the side effects make the whole experience really bad, so they don't want that one anymore, and they'll switch to another. Yet it hit the market, right? So on average, it's supposed to do well. If you don't include these little side findings, these kind of important but not overall findings, you won't be able to identify the right groups of people to use those drugs for. Okay, so that was Chapter 9.